It was Robert Louis Stevenson who said, "For my part, I travel not to go anywhere, but to go. I travel for travel's sake. The great affair is to move." In this lesson, we're going to measure dispersion using standard deviation units. We're going to compute z-scores. We're going to find percentages using normal curve. And we're going to compute raw scores using z-scores. All to be able to answer the question, how can graphs help describe frequency distributions? To make sure we're ready for this lesson, let's take a look at warm-up number 2. Find the y-intercept of the straight lines with the following equations. And first up is y equals 9x minus 11. Now this is the standard y is mx plus b, where b is the y-intercept, so negative 11. Now looking at 7 plus 3x. We get the same thing. That 7 is the b value. The third one, 3y is 6x plus 12. We need to divide each of these things by 3, giving us y is 2x plus 4, and now we can see that 4 is the y-intercept. Now let's take a look at a problem that you will be able to do by the end of this lesson. Now a local travel magazine rates hotels using integers from 0 to 100. Last year they rated over 2,000 hotels. The ratings were normally distributed with a mean of 78 and a standard deviation of 6.5. How high would a hotel rating have to be for it to be considered a top 10% rated hotels? Top 10% means we're looking for 90% or 0.90. The question becomes which of these is actually closer. 0.89973 is closer to 0.9 than 0.90147. This looks closer, but it is in fact a little bit farther away. So we're going to go with a 1.28, meaning 1.28 is going to be equal to x minus 78 over 6.5, giving us x minus 78 being equal to 8.32 or x being 86.32. Americans are always on the move. We love to travel, especially in the summer when school is out. In the winter, we love to travel to warmer destinations or go skiing. What are the most popular destinations? How do these popular destinations plan for the correct number of visitors? How much do people spend on souvenirs? Why do hotel prices change during different travel seasons? There are many variables travelers and businesses need to take into account to make vacation plans. Consumers need to anticipate costs, and the business need to anticipate how many visitors they will have. They can all use statistics to aid in their planning. You might have heard the expression, a picture is worth 1,000 words. In statistics, graphs of distributions are like pictures that describe large quantities of data. Imagine you list everyone in the United States and their income. The list would be too cumbersome to interpret. Imagine a table of essential expenses of households in Florida. Think about how measures of central tendency and dispersions could help describe that huge volume of data in a much more user-friendly way. Now, you have already learned about percentiles. Percentiles are commonly used because the raw data, the actual number, don't provide any comparisons. For example, you hear that 100 students visited the Grand Canyon. You have no frame of reference. If 100 students in an elementary school of 240 students visited the Grand Canyon, that makes it look like the vacation destination is very popular. But if only 100 people in the state of California visited the Grand Canyon, then that would mean the destination is very unpopular. Notice how the raw data without reference is tricky to try to interpret. However, if on a snowy day 80% of the students in your school slipped and fell on ice, there is a major danger that must be dealt with. If 1% of the students fell on ice, the problem is not nearly as severe. There are commonly used graphs in statistics that use percentiles to solve. It is prevalent because it accurately portrays the behavior of many real-life data distributions, and as a result, it is called a normal curve. In the first 3 lessons, we learned about the advantages and disadvantages of different measures of dispersion. In the beginning of this lesson, we're going to learn how raw data is different to interpret because it lacks a frame of reference. To start that, we're going to take a look at z-scores. If a score is 10 away from the mean, the standard deviation is 2,000. It is relatively close to the mean. If a score score is 10 away from the mean and the standard deviation is 2, then the score is very, very far from the mean. So knowing the value of the standard deviation does not tell you the whole story. For this reason, we're going to use standard deviation. To convert raw scores into a measure called the standard score, since this is based on the standard deviation. The standard score uses the standard deviation as a unit. It gives the number of standard deviations a number is from the mean. The standard score is called the z-score for short. It makes sense to measure the raw score in terms of standard deviations from the mean. Now let's compute some z-scores. A summer camp is taking 220 sixth graders on a trip to an amusement park. For safety purposes, some of the rides have height requirements. The campers' heights have a mean of 56 inches and a standard deviation of 3 inches. What is the z-score for a camper with a height of 62 inches? The raw score will be represented by x. We're going to use the Greek letter mu to represent the mean, just as we used the Greek letter sigma to represent deviation. So x minus mu. Now we're going to divide all of that by the standard deviation to find the z-score, with the camper's height being 62 and the mu being 56. Now they gave us a standard deviation already of 3, so we simply substitute those values in and do those calculations to get a z-score of 2. The z-score for the raw score of 62 is 2. This can be interpreted as 62 is 2 standard deviations above the mean. You can think of the standard deviation as a unit of measure whenever you work with z-scores. Now let's check our understanding of this, and a camper on a trip has a height of 54 inches. Express the height as a z-score and round to the nearest hundredth. So we already know that z is x minus mu divided by sigma. Some of the information that we know is they're asking about 54 inches from mu of 56 and sigma being 3. 54 minus 56 gave us a negative 2, and this is over 3. So it represents 2/3 of a standard deviation. Now let's compute a raw score using z-scores. A summer camp is taking 226 graders on a trip to an amusement park. For safety purposes, some of the rides have height requirements. The campers' heights have a mean of 56 inches and a standard deviation of 3 inches. The height of certain students is a z-score of negative 0.5. What is the student's height in inches? So we know that z is negative 0.5. We do not know their score, but we do know the mu is 56, and we know that the sigma is 3. So now we have a just solve for x type problem, meaning x minus 56 is a negative 1.5, or that x is 54.5. So the z-score of negative 0.5 corresponds to the height of 54.5 inches. Let's check your understanding. The distribution of money the campers spend on souvenirs has a mean of 12 and a standard deviation of $1.20. Find the amount spent by specific camper who had a z-score of 1.5. So if their z-score is 1.5, this is going to be equal to x minus 12 divided by 1.2, or that x minus 12 is equal to, 1.5 times 1.2, which is 1.8. Adding 12 to that, we get that x is 13.8. A normal curve is a graph of a normal distribution, and since it reflects so many real-life variables, it is often used in the natural and social sciences to depict the distribution of certain variables. What does the curve look like, and what are some of the characteristics? A normal curve is a bell shape and is often called a bell curve. The middle scores represent the mean, and the mean is equal to the median in a normal distribution. Most of the scores cluster around the mean. They are very close to it. Fewer scores occur as you get farther from the mean. The curve is asymmetric to the horizontal axis. This means the ends of the curves, called the tails, get closer and closer to the horizontal axis as you move away from the mean. They never touch the horizontal vertical axis. The area under the curve equals 1, which represents 100% of the data in the distribution. Notice that 50% of the data is above the mean and 50% is below on a normal curve. The area in any interval under the curve represents a percentage of data that is within the interval. To find these areas, you will need to use z-scores and a z-score table. Let's find a percent using normal curves. Let's recall the amusement park from example 1 and example 2. A certain ride requires riders to be at least 51 inches tall. The heights are normally distributed with a mean of 56 and a standard deviation of 3. Approximately how many of the camp's 226 raters will not be allowed on the ride? You will need to compute the z-score and use this table off on the right. First, draw a sketch of the bell curve and label where the mean and where the height of 51 could be. Shade the area under the curve below 51 inches. This area represents the percentage of campers who are shorter than 51 inches. Next, let's convert it to z-score. So 51 minus 56 divided by 3. This means we get a z-score of negative 1.67. We can see negative 1.6 on the left side, and when we track that all the way over until we find that 0.7 and track that all the way down, there we get 0.475, which as a percent is 4.75%. Therefore, you can expect 4.75% of the students to be less than 51 inches tall. Since 4.75% of the 220 is 10.45, and you can't interpret a fraction of a student, you can round and say that approximately 10 of the students will not be able to get on the ride. Let's check your understanding and use the data from that example. If another ride requires riders to be 60 inches tall, what percentage of campers will be able to go on the ride? Now that z minus mu over sigma, that's for everything underneath it. What we're looking at is what's going on above it. So now we're going to use mu minus x over sigma, or 56 minus 60 divided by 3, giving us a negative 1.33. On the table, negative 1.33 intersect at 0.918. Now 0.918 is 9.18%. Let's extend our understanding by using the data from example 3 and find a percentage of students who will be able to go on the ride that requires a height of 51 inches. Now, if it requires 51 inches and we know that the average is 56, we also know that the standard deviation is 3, so we get a z-score of negative 1.67. By using the table, finding negative 1.6 and a 0.7, we get a 0.475, which is 4.75%. Now, this is the percent that cannot go on the ride. With 100% of the students that are there, if we subtract that 4.75%, we're left with 95.25% that can go on the ride. Now, let's measure dispersion using standard deviation units. Families of students at Smithtown High School were surveyed about their vacation expenses. The results were normally distributed with a mean of $2,313 and a standard deviation of $390. What percent of families took vacations that cost between $2,000 and $3,000? Up first is to think about that $2,000 one. So $2,000 minus 2313 divided by 390 will give us approximately negative 0.80. We can see that this gives us a 0.2119. And taking a look at the 3,000, all we do is use 3,000 as the x variable, doing all of the same calculations, and we get approximately 1.76. So that's going to give us a 0.96080. So 0.96080 minus 0.2119 will give us approximately 0.7489, or 74.89%. Let's check our understanding of this and use the data from the family's vacation expenses in example 4 to find the percent of families that had a vacation expense between $1,000 and $2,000, rounding to the nearest percent. So up first, looking at the 2,000 and doing a little bit of calculation, we get a negative 0.803. This gives us a 0.2119. When we do this for the 1,000, we get approximately negative 3.37, which gives us 0.0004. So when we take 0.2119 and subtract 0.0004, we get 0.2115, or 21.15%, meaning 21%. Now, a local travel magazine rates hotels using integers from 0 to 100. Last year, they rated over 2,000 hotels. The ratings were normally distributed with a mean of 78 and a standard deviation of 6.5. How high would a hotel rating have to be for it to be considered a top 10% rated hotels? Top 10% means we're looking for 90%, or 0.90. The question becomes, which of these is actually closer? 0.89973 is closer to 0.9 than 0.90147. This looks closer, but it is in fact a little bit farther away. So we're going to go with a 1.28, meaning 1.28 is going to be equal to x minus 78 over 6.5, giving us x minus 78 being equal to 8.32, or x being 86.32. Let's check our understanding and use the travel magazine statistics from example 5 to find out what the hotel's ratings would have to be below ranked in the lower quartile of hotels, and round that to the nearest integer. So we're looking for 0.25, and the closest we can get to that is 0.2483. This means we're going to go with a negative 0.68. So negative 0.68 is going to be equal to x minus 78 over 6.5, meaning negative 4.42 is going to be equal to x minus 78, or x is equal to 73.58.